like I was mentioning, health monitoring systems, we're looking at self-monitored systems where we can intervene if there is some issue, or human body is a prime example of it. And health monitoring and monitoring systems in general have been implemented to a great level of sophistication in aircraft structures and a lot of aerospace structures. Now, in comparison, civil engineering structures tend to be cruder. While we talk about health monitoring, the level of application is not to the same extent as you would see in perhaps the aircraft structures. Just to give you a background first of what we are dealing with, what is the material that we're dealing with in concrete in particular, it starts out in a fluid state. So when you mix concrete, it's in a fluid state. It basically resembles a fluid, but it's not like any fluid that you would see. It's basically like a very thick suspension, but it flows. And basically, because it's a fluid, it doesn't retain shape. So we basically give it a shape by putting it into formwork. So what you see here is a formwork, the shape that you want to give the material. You pour it into that formwork. And then slowly with time, concrete ages. So it transforms itself from a fluid state to a solid state, and the solid slowly gains strength. Once concrete is strong enough, we remove the formwork, and then what you see is this concrete structural element. So you see the beams and the columns and the concrete slabs. So there's a complete transformation that takes place. It starts out in a fluid state, ends up in as a solid, and the solid slowly gains strength over time. So that's the life cycle of the production part of concrete. Then, of course, the building comes in service. So what you see here is the building that is still in construction. Once it has completed construction, it comes in use. And of course, typical concrete structures are built for 50 years or 75 years or 100-year lifespan. So we expect the concrete structure to give us good service performance over that span, over that time period. So we are talking about, when we talk about time scales, let's say this is the times 0. This is when I mix concrete. This is when it's in the fluid state. To a time scale in days when concrete is basically sitting in that formwork, slowly going through the transformation, to months when the concrete structure is being completed, to years when the building comes in service. So these are the time scales we're talking about when it comes to concrete structures. Now, typically in concrete, if you look at what happens in concrete, small cracks initiate in concrete very early in the life of the structure. And these cracks are very small. They are basically oftentimes sub-micron level cracks which are formed in the concrete structure. And that happens on the time scale of days. So that basically this happens while concrete is still fresh, it's just been cast, it's still in the formwork, oftentimes cracks do form. And even while the concrete structure is being constructed, oftentimes these cracks grow, they become larger. And once the building comes in service, these cracks become larger, and then that's when we start seeing this cracking in concrete structures. So now the issue is, so what are the concrete structure cracks? Now the problem with concrete is that once a crack forms, water can get into concrete, and typically concrete structures have steel. What you see here is the steel reinforcement. The reinforcement starts corroding, and then we have major issues in terms of damage that starts happening to the concrete. Once the steel starts corroding, the capacity of the structure, the structural capacity, the strength starts degrading. So this is what we are looking out for. So when we're talking about monitoring of a concrete structure, ideally the monitoring should start somewhere here. It should start just as we are pouring concrete, and it should continue over the entire life of the structure. So this is the motivation for what we are doing here at IIT Hyderabad in trying to develop these embedded sensors for concrete structures. And of course, if we wait for too long and the damage is very severe, we'll see pieces of concrete falling off, the capacity of the structure gets degraded. So in terms of structural health monitoring of the concrete structure, keeping in mind these different stages, concrete starts out as a viscoelastic fluid suspension, then it basically changes into a solid. Initially, it's like a porous solid, it gains strength. That's at that stage, we call it mature concrete. That is usually after about 28 days or so after casting. And then cracks form. So basically the formation of cracks takes place in this stage itself in the matter of few days. Those cracks, when the building is in service or when the structure is in service, slowly grow. And eventually, of course, if we don't attend to those cracks, we can have failure of the concrete structure. Now, the issue of monitoring of concrete, when we're talking about fluid state, mostly what we rely on are dynamic oscillatory shear measurements, but they're basically laboratory-based measurements, primarily rheology-based. We have mechanical measurements. We use vibration-based measurements once the concrete has become a solid. So, and then of course we can do mechanical testing, but again, these are not in situ. So they're typically, you take a sample from the structure and test it in the lab. Although vibration-based measurements can be applied to the structure as a whole, they're used typically for structural health monitoring measurements. There are ultrasonic measurements which basically give you the entire gamut of measurement, but typically the way we apply them they can be done in situ, but they're basically done surface-based measurements. We don't get to know the health of the material from the inside. So this is where PZT sensors, especially if we can develop embeddable sensors, would fill that gap and basically allow us to cover the entire time scales in the operation of a civil engineering concrete structure. So now, getting to the background of piezoelectric effect, I'll just quickly browse through there. Here we're talking about a material where basically the electrical and the mechanical components are coupled. So if we apply a mechanical stress on it, it will generate a voltage or a potential difference across the faces of the material. And if you apply a voltage, will basically produce a change in shape, or there'll be some mechanical strain. So in terms of constitutive relationship, you see that the mechanical and the electrical components are coupled. So you get these off-diagonal terms are non-zero. So that is the interesting part of this piezoelectric material behavior. And what we specifically look for is how this material behaves when we apply an electric charge to it. So if I apply an electric charge to it, I'll produce a strain. So basically the material will undergo a change in length, or there'll be some strain that is induced in the material. Now, of course, we are interested in electrical measurements, and we apply an AC current or a voltage to the PZT material. What we are essentially monitoring is to either get the admittance or the impedance measurement from the PZT. So simplistically speaking, we are measuring the relationship between the current passing through the PZT and the voltage applied across the ends of the PZT. And of course, it results in a complex behavior because the current and the voltage are never in phase. So we get basically a complex relationship of either the admittance or the impedance. Essentially, admittance is the inverse of impedance. So now if I look at a PZT, suppose PZT is typically available in the form of patches, and we use a PZT patch in monitoring. So if I look at, say, a patch, this is a typical size of a patch that we use. It's about 20 millimeters by 20 millimeters and 1 millimeter thick. And we hit it with an alternating current. And suppose I sweep it through the frequency, what we would see as a response would basically show this kind of a response. What I'm plotting here is the admittance signature. So this is the modulus of the admittance. And you would see these peaks stand out. And these peaks that you see in the admittance response, these peaks are basically correspond to resonance modes of the PZT patch. I'll just show you this. But before we do that, remember that admittance is a complex measurement because the voltage and the current are not in phase. So we get the conductance, which is the real part of the measurement, and the susceptance, which is the imaginary part or the out of phase component of this measurement of admittance. Now coming to, if you look at the conductance here, we see that, of course, these are peaks. These are the same peaks as what you see in the admittance here. And you can see that there are these distinct peaks in the response, conductance response, when I plot it against the frequency of the applied excitation. So here we are applying a voltage across the PZT, but we are sweeping it through the frequencies. Now, just to show you what I imply, this is the first resonant mode of the PZT patch. So basically, it will vibrate and with that particular mode shape. Then mode 2. This is the mode 2 of this particular patch. This is the third mode. So you can see that these modes get more and more complex. Basically, each mode to us signals that this is where the energy of the PZT is basically the maximum. So when I'm looking at either sending or putting energy into some material, this is where I would like to be centered on in order to be sending, transmitting energy. And by the way, PZT patches are used in developing or in making ultrasonic transducers, and we try to send sound waves. This is what we try to rely on. Now, the frequencies of resonance themselves depend upon the geometry of the patch. So if I make the patch smaller or bigger, I can basically alter the modes, the eigenfrequencies or the frequencies at which these resonant modes occur. Now, so just going along with the different modes, you see that the mode shapes get more and more complex. So in monitoring and using these PZT patches in structural health monitoring, suppose I embed a PZT inside concrete, or I put it inside some material, and I do the same thing again. That is, I apply the potential across the PZT patch and I sweep it through the frequencies. What I would find now is that the PZT would still try to oscillate or vibrate inside the medium, except now its vibration signature would be altered because now it's no longer a free PZT. So a schematic representation of that would be like what I've shown here. We have the PZT on across which we're applying the voltage, except now the PZT is coupled to a substrate, or it's basically coupled to some material around it. Now, depending upon the mechanical impedance of the material, the resistance given by the material, the resonant mode, the resonant behavior would change. And now if we can unlock what is the change in the resonant behavior of the PZT, then we can actually infer what is the mechanical impedance offered by the material. The mechanical impedance of the material, which is given by this term Z subscript S, would in turn depend upon the elastic modulus or the Young's modulus of the material, its Poisson's ratio, and its damping. So inherently what we have, once we have this PZT sitting inside a material, is a way of unlocking the stiffness of the material, because the behavior of the PZT would be altered depending upon the stiffness of the material. Now, of course, the key would be to unlock this relationship, is to somehow figure out what change is produced in the dynamic response of a PZT depending upon the mechanical impedance of the material. So this is one of those things that we do use in health monitoring. And unlike other materials, I have a choice of embedding PZT inside concrete because it starts out like a liquid. So I can simply stick it into the concrete and let the concrete harden around it. And what I have now is a listening post. I have some material, essentially a PZT patch sitting inside concrete, which basically I can probe by applying this potential, and from there I can infer about the health of the material around in the immediate vicinity of the PZT patch. So that's a basic principle of what we use in health monitoring of the of concrete structures, essentially inferring about the mechanical impedance of the concrete surrounding the PZT patch. So, but the one thing we've, of course, through our research found out is that the sensing area is localized. So, basically, it's like a full space problem. If I have a point source, you can treat PZT like a point source. Only a certain area around the PZT would be influential, would be influencing the behavior of the PZT. So, once we establish what is that area that it is sensing, we can use it like a local sensor, local probe of the material in the immediate vicinity of the PZT patch. Now, the other thing that we can do with the PZT patch is that because it can vibrate, if I hit it with an electric voltage, and if I can hit it with an electric voltage of, let's say, a certain frequency, the PZT will faithfully repeat that and send waves into the material. So as the PZT vibrates, it basically transmits energy into the surrounding material, which propagate as stress wave in the material. Now, the stress waves, I could use stress wave based monitoring of the structure. So now if I have, let's say, two PZTs, one which I can use an actuator, which I hit with a voltage, would generate the stress wave into the material. And then the other one, once the stress wave comes and hits the PZT, the other PZT patch, because the stress wave as it impinges on the PZT would basically produce a straining effect on the PZT that would produce a voltage in the other PZT. And so now if I can monitor the PZT across the two terminals of this sensor, which is basically sitting in the path of the stress wave, I can actually capture the stress wave going through. So what I have is now a pair of PZTs, one which is an actuator, which I'm hitting with an electric voltage to generate stress wave, and another which is a receiver, which basically sits and listens to, passively listens to the stress wave. So I have an actuator receiver pair for transmitting and receiving stress waves in the material. So this is another way that I could use these embedded PZT sensors once they are located inside the concrete. And of course, if a stress wave is going across and there's a change in the material medium, that would be reflected in some change in the stress wave. And once, if I can unlock that, the what is the causal effect and how stress wave changes are produced by, let's say, something like a crack, then I can do an inverse problem and infer what is the opening of the crack and other details. If there's any damage in the material, I can use that to infer about the local the state of material in the path of the stress wave, which is with these two stress wave transducers. So now next what I want to talk about is the evaluation of this PZT sensor, which is embedded in concrete. We've actually developed an embeddable PZT sensor. So this is using PZT patches. Basically we've developed a protection mechanism which allows me to protect the PZT patch, because when I put it in concrete, concrete is a water-rich medium, so I have to prevent this PZT from short circuiting. So we apply an epoxy layer that's applied by spin coating. And then we have also coated with a hydrophobic coating, which is just a few microns thick, just to protect the epoxy layer, because the epoxy layer or epoxy itself is sensitive to moisture. So to protect it, we apply a hydrophobic coating, a spray on top of this epoxy layer. So this is the physical size of the PZT sensor that we have, and we can embed it into concrete and use it in those two modes that I was talking about. So initially what I want to do is talk about what would happen if I put it into concrete and look at the behavior in the impedance measurement. So here what we're doing is basically, essentially, I have the PZT sensor sitting inside concrete, and we apply an electric voltage of multiple frequencies, and then try to get the admittance response. And specifically, we are more interested in the conductance response, the real part of the admittance. So here, what I'm showing you is, of course, the resonant modes of the PZT. The black line shows the resonant mode of the free sensor. That is, if I, or the free PZT. If I look at the PZT by itself, and the red line is the the red line is the line for the free PZT sensor, and you recognize all the resonant modes here. The black line is the PZT sensor. This is the PZT with the epoxy coating and the hydrophobic coating on top of it. You can see there's a small change in the resonant frequencies and the amplitudes as well, but essentially all the resonant modes remain intact. So it's still usable. Now, we are more interested in, basically, this is the most dominant mode. This is where I have the maximum energy. So we basically focus our attention on the first mode of this PZT sensor. And let me show you how this, what happens when we put it in concrete. So this is a typical composition of concrete. This is the conductance, the spectrum corresponding to the first mode. So this is the, you see the peak here. This is the first mode signature. And with time, how this signature is changing. So you see, if I immediately after putting the PZT sensor into concrete, there's a drop in the amplitude of the conductance, and there's a slight leftward shift in the frequency, central frequency of this first mode of vibration here. Now, if I wait with time, you see that the amplitude starts decreasing. So that means, and this is, of course, we've done up to 3 hours. So after mixing of concrete in the first 3 hours, after I stick it into this concrete block, these are the changes that you start seeing. Now, if I wait longer, so this is the recording between 3 hours and 9 hours. You see that very rapid changes start taking place. So now in this graph here, you see this is my reference here. This is the PZT sensor as it was in air. This is the recording at 3 hours. Now with time, you see that there's a continuous change in the resonant mode. It's getting broader. It is shifting rightward, so the rightward shift in the frequency, and there's a continuous drop in the amplitude. Now, if I wait, go up between 12 hours and 28 days, this is my PZT sensor, the first mode. You see that there's a continuous drop, so it continues up to 28 days, and there's a continuous rightward shift in the frequency. So the resonant mode of the PZT sensor or the PZT patch is continuously changing. And if you recall, that change happens when the medium changes. So basically, initially, the medium is in a fluid state. So it's basically like a soft material. So the PZT vibrates, is not much of a change in its behavior. But then as it changes state, so between this 3 and 12 hours, the change of state that's happening. it goes from a liquid to a solid. By the time 12 hours happen, the concrete has become a solid. It's still a weak solid, but it is a solid. So you can see that during the change of state, there's a very rapid drop in the amplitude and a rightward shift in the frequency. And that continues as the solid is getting stiffer and stiffer. So the Young's modulus of concrete is increasing. It is basically getting stiffer. You see that there's a further continuing change. So the aging medium of concrete basically produces this change. So now the question is, how do I back out the stiffness of the material from here? So just to show you data collected from multiple specimens. And basically what we've done here is to look at this data here and basically separate out what is the change in the amplitude, how much drop has taken place, and what is the shift in the frequency, how much frequency shift has taken place in this peak here. So these two are plotted here. So you see the conductance, this is the amplitude of the conductance. So there is basically an initial drop here when I stick the PZT into the concrete. Then it stays flat for some time, and I'll explain that in a few minutes as to why initially in concrete it stays flat. Then there's a rapid drop, and it essentially goes into this asymptotic kind of a behavior. Similar thing happens with the frequency. So this is over a period of about 28 days. You see that there's a very rapid change here. Then it becomes slower, and it settles into this slow asymptotic change after that. So the insets show you what is happening in the early part. So in the first 24 hours, what is the change that is recorded is shown here. So now, just to show you to correlate things here, initially when I measure the conductance, we're talking about the amplitude that I measure. Initially, the concrete is in a fluid state here, and then it goes through setting. This is where the transformation is happening. It is slowly transforming into a solid, and then by about 7-8 hours, the transformation is complete, and then it starts as a very soft solid, which slowly gains in stiffness. So as the stiffness is increasing, there you can see that there is a continuous decrease in conductance, and there's a continuous increase in frequency. So with this now, the thing was to understand what would happen if, how do we unravel this? How do we try to determine the material changes in the concrete? So for that, we of course, because this is not an easy problem to do analytically, we had to resort to simulations where we're using COMSOL multiphysics. First thing is to using this particular software is to mimic the behavior of the free PZT, and that we were able to basically mimic the free PZT behavior. So that gave us confidence that at least we had a good understanding of the module that we were using. And then to basically put it into concrete, where we model the PZT sensor, the PZT, the epoxy surrounding it, and stick it into concrete. And now we can start playing with the properties of the concrete by increasing the Young's modulus, the Poisson's ratio, and all these properties of concrete to see what kind of changes could be produced. So basically, first thing we tried was to look at the influence of damping. Now, if I increase the damping of the material, what we see is a downward shift in the amplitude and a leftward shift in the frequency. This is what damping produces in this signal or in the resonant behavior of the PZT. Now, if I look at what happens to increasing the stiffness of the material, so if I basically let the concrete gain in stiffness, I start with a very small value of modulus of elasticity of 0.0001 GPa. So it's a very, very soft material, a very, very soft solid, and progressively increase the elastic modulus, the Young's modulus of the concrete. What we see when we did the simulations is basically something very similar to what we observed experimentally. As we increase the the Young's modulus of the material, basically one would see a downward shift in the amplitude and a rightward shift in the frequency. So that basically gave us a good handle on that we were on the right track. At least we were that what we are observing is related to changes in the concrete material medium as it is brought about by aging of the material. So this is the conductance, change in the conductance and the increase in the frequency that we were able to simulate from the COMSOL presentation, which looks very similar to what we had seen in our experimental result. Now, we basically, we often get asked this question that it's one thing to do the simulation, but how do we know that the first mode of the PZT that we were tracking there, that mode itself doesn't change? Because as the stiffness of the material surrounding the PZT changes, it's likely the modal signature or the modal the eigen vector itself may change. Just to satisfy ourselves, we basically did this simulation with different stiffnesses of concrete. First, the free PZT, this is the displacement signature. PZT with the epoxy, which is the sensor, you can see here. When concrete is very soft, with a very low Young's modulus, and even when concrete is very stiff, which is typical of mature concrete, 30 GPa, we see that the signature doesn't change, which indicates that the first mode essentially is not altered as the material around the PZT is aging. Now, then we wanted to understand what happens when we put this PZT patch into the concrete and let the material concrete age around it. And aging means that it's basically gaining in elastic Young's modulus. So what we find and what we're tracking here is the displacement of the epoxy. So we have this is the epoxy, this is the PZT. We're tracking the displacements of the corner of the epoxy. Now this is the boundary of the sensor, and this is the PZT patch inside. And this is the layer of epoxy around it. This is the displacement that we track of the epoxy around the PZT. And this is the displacement of the corner of the PZT. And what we find initially when the concrete is very, very soft, the Young's modulus is very, very low, basically the epoxy acts like a rigid body. The PZT pushes it gets pushed into the concrete. And so it just basically, the total, the displacement between the two is basically large. But as time goes and when the stiffness of the concrete increases, we find that the movement of the PZT, once the concrete becomes stiff enough, and let's say the concrete becomes around half a GPa or 1 GPa in Young's modulus, then the movement of the PZT is restricted to within the epoxy, because the stiffness of the epoxy is around 1 to 2 GPa. So what happens then is, once the concrete becomes stiffer than the epoxy, then as the PZT vibrates, it's essentially getting pushed into the epoxy, and its movement is limited to within the epoxy layer. That's what we are getting here. So there's a change in the dynamic, but essentially we are able to track the movement of the corner of the PZT within the within the concrete. So just to give you a schematic representation. So initially when the concrete is very, very soft, PZT has its way. It's basically able to push the concrete aside. But when concrete gains in stiffness and concrete goes from something which is like, which has Young's modulus of a few megapascal to about 30 to 40 gigapascals. So at that point of time, then concrete and PZT are quite matched in their Young's modulus. So it's a competition of equals. And at that point of time, then the movement of the PZT is taking place within the epoxy layer. So we were able to come up with a conceptual representation of this PZT sensor embedded in concrete. And basically, this is the conceptual representation where we have the mechanical impedance of the PZT. The epoxy they is split into two parts, the local and the global. The global is basically like the rubber band effect, which is holding the PZT patch. The local is this effect where the epoxy itself gets compressed when the concrete becomes soft, when the concrete becomes stiff. And then the mechanical impedance of the concrete is basically represented in terms of its Young's modulus, its Poisson's ratio, and its damping. So from here, what I want to now talk about is how these changes take place in concrete. Typically, when we are monitoring concrete changes in concrete produced by the chemical reaction that's taking place, we monitor it using what is known as isothermal calorimetry. We measure the heat released from concrete. And the heat release basically conveys about the rate of reaction. So I will just show you some data from the concrete, which is collected with different compositions. And we were able to basically get an idea of the mechanical impedance of the concrete surrounding this PZT patch for different varying compositions. And basically, we were able to back out the Young's modulus of the material and match it with the effective impedance of the concrete medium that we were able to determine from the vibration signature of the PZT. So what you see here, these are basically graphs of concrete with different compositions. And we find that the Young's modulus of the concrete, which is measured using a different technique, which is basically a vibration-based technique, we were able to match that very closely with this effective mechanical impedance of the material medium that we got from the measurement using the embedded PZT. So basically now we have a local sensor which gives us an idea of the change in stiffness of this concrete material sitting from a sensor that is sitting inside the concrete. Next thing is to look for vibration measurement. So now that I have this PZT sensor, it's sitting in concrete, the concrete is hardened. Is it possible to use these to pick up vibration signatures? So what we did there is to now put these PZT sensors inside concrete, inside a concrete cylinder, and then to see if we could pick up the vibration that is produced by an impact of a small steel ball. And we did the modeling just to understand what are the different modes of vibration that are produced. And we also had a surface mounted accelerometer, which basically picks up, which is typically used for vibration measurements. So just to show you, this is the vibration signature from the embedded PZT sensor produced by this impact. And this is the signature that we get from the accelerometer. If we actually look at it in the frequency domain, we were actually able to get the modes of vibration of the cylinder very accurately using these embedded sensors. So that basically told us that we could actually use the PZT sensors even to pick up ambient vibrations, or we could pick up vibrations produced by impact, or which is either natural or induced vibrations because of impact by an external body. We could basically use these PZT sensors in health monitoring or vibration-based health monitoring once they're embedded inside concrete. So just to show you that basically we did this experiment where we backed out, because we can use the frequency signatures to calculate the Young's modulus and Poisson's ratio of the material, because essentially these are the two elastic material properties that determine the vibration signature of any finite geometry. So then we've used the cylinder geometry, backed out the Young's modulus, and we were able to basically track the Young's modulus of this aging concrete as concrete is aging using these embedded PZT sensors, and it matched perfectly with the known procedures that are available with ASTM. So that gave us confidence that this embedded sensor can now also be used for vibration monitoring sitting inside a concrete structure. Now, the next thing is to see that can we use it for monitoring damage. So we can now monitor this aging material, where we can pick up the changes in the mechanical impedance of concrete as it ages. We can use it for monitoring vibrations. Once the sensor is sitting inside the concrete structure, it will pick up vibrations, and we can use it in vibration monitoring based methods. So now next thing is to see if we could monitor damage in the material. And basically, to monitor damage, we wanted to use both the EI, which is the electrical impedance based measurement, and the wave based measurement. So I'll show the impedance based measurements first. We have a PZT sensor sitting inside concrete onto which we are applying a load. Now, if there is damage present inside the material, it should affect the compliance of the material or the mechanical impedance. The mechanical impedance of the material should decrease if there is damage in the material, or the mechanical compliance of the material should increase. Material becomes more compliant. And the damping of the material will increase, because as the material, there's damage induced in the material, there will be larger damping. So these are the two effects that I expect. But there's a small complication, and that is, when I have a concrete structure and damage is induced, typically concrete structures are loaded. So there will be load or stress that's already in the material. Now, the issue is that PZT materials have coupled electromechanical response. So if there is stress, I expect that that will also have an impact or some influence on the signature or the EI response of the PZT. So basically, what we need to do is somehow to decouple the effect of the stress in the material medium from the damage in the material medium. And the third thing to think about is that concrete has different forms of damage. If I apply compression, damage is produced in the form of several cracks, as you see here. And basically that results in a disintegration of the material. Whereas if I apply tension to concrete, damage takes place in the form of a single crack. So the forms of damage are very different depending upon the stress state. So looking at compressive stress state, what I expect to see is damage in the form of several cracks, which basically initiate from micro cracks, and eventually that they form and it produces disintegration of the material. So basically, we did an experiment where we put concrete inside this cube. We put this PZT sensor inside this cube of concrete, and we applied load, except we applied loads in cycles. We would basically take the ultimate load, the maximum load that the cube can take, which is based on the failure stress of the material, and we ramped the stress up to 10% of that, unloaded it, 20% unloaded, and 30% unloaded. So we incrementally increased the loading on the specimen. And every time we were loading it, we were taking a reading here, and even in the unloaded state. Reason we were doing this is, whenever I take a reading in the loaded state, that reading is influenced by damage in the material and also stress in the material. Whereas when I take a reading in the unloaded state here, that reading is only influenced by the damage because the stress has essentially been removed. So if I look at the loaded and the unloaded states, I can then infer what is the change that is produced by the stress in the material and what is the change that is introduced by the damage in the material. So this is what the loading response looks like, and you can see progressively there's a change in the stiffness. So this is the initial stiffness, and as I continue loading, you see that the secant stiffness continues to decrease, and secant stiffness decreasing means that there is damage accumulating in the material. So this is, we were using DIC just to track damage, just to see when would damage be visually apparent. So the damage basically in the form of cracks was visible once we went to about 60% of the ultimate stress. So up until that point, there was no damage that was visible, and you can see these cracks that are starting to form. And as I increase the loading, basically more and more cracks start to form. Eventually, the material disintegrates. Now, just to show you what would happen to the response, or what was recorded in the unloaded states, what happens with damage. This is the secant stiffness in the different loaded states here. So you can see that with every passing cycle, once I go beyond 40% of the ultimate, the secant stiffness starts to drop off very rapidly. And secant stiffness dropping off rapidly means that there is damage accumulating in the material. So now this is the baseline signature. This is a signature collected after 20%, 30%. And you can start seeing changes start happening after 40% of the ultimate stress. So that means there is damage that is happening at 40%, but there's nothing visible on the surface of the specimen. Nothing was seen. So there is internal damage, but it is not visually apparent. It cannot be picked up even by a very sensitive DIC measurement, where we had submicron level measurement accuracy in terms of displacement. And after 50-60% is where we start seeing a shift, a steady shift. The interesting thing to note here is that this change that we're seeing is because of increase in damping of the material, and also because of an increase in compliance or a decrease in stiffness of the material. And we see that that basically produces a downward shift in the amplitude and a leftward shift in the frequency. So now if you remember in the simulations that we had done, as we had increased the damping of the material surrounding the PZT sensor, it produced a downward shift in the amplitude and a leftward shift in the frequency. So basically this is the right indicator that as damage increases, this is what we expect to see. Then these are the changes that we got in the loaded state. So as we start loading, now remember, these are the changes we're getting as influenced by stress and damage, because these are the loaded states. And so we see a continuous decrease even at a very low load state, because there is a change that is produced by the stress in the material. And we see that basically it's a continuous rightward shift and a drop in the amplitude. So now what we have is a way of segregating these two effects in terms of the changes produced by the stress in the material and the changes produced by damping in the material, the damage in the material. So this is what we are using to basically determine the level of distributed damage in the material produced by compression, because compression produces distributed damage in the form of multiple cracks. And basically with this now, we are trying to segregate the effects of stress, change of stress in the material, and change in the damage level in the material. So now, irrespective, what we were able to get from here is that we're able to detect damage or stress in the material at a very, very low stage. So you can see that even at about a stress state of over 10% of the ultimate, we are able to pick up the stress in the material. Similarly, we are able to pick up damage at its inception. At about 40% of the ultimate stress, we were able to pick up that in the impedance signature, while it took much longer till close to 60 to 70% of the ultimate when the visual, when the damage was visually apparent. Now, the final thing is we looked at damage in compression. Next thing is to look at damage in tension. Now, when we have tension in concrete, then basically we expect to see a single crack, a localized crack forming. Now, to simulate that, we tested a beam, a concrete beam in 3-point bending, and typically what we expect to see is a single crack to form here and progress along this the length of the beam, eventually splitting the beam into 2 pieces. So basically the loading protocol that we followed was very similar to what we had done before, where we basically did this loading unloading cycles where we went and loaded the beam to different load levels. In this case, what we were doing was carefully monitoring the crack using a CMOD, or a crack mouth opening gauge. And we were opening the crack in a very controlled manner. So we basically opened the crack to 40 microns, then to 80 microns, 160 microns, and so on. So we were basically incrementally increasing the crack mouth opening displacement. And this is the arrangement of PZTs that we had. So we had PZTs around placed in the concrete, and the idea was to use them as actuator receiver pairs, where one would be the actuator, and we had multiple receivers, so we could basically see what was the change that is produced by the stress wave emitted by one, and when it would be received by the other. So here we have, like I said, one actuator, multiple receivers, and we have the setup where we are very carefully controlling the crack as it's forming in this beam, because we wanted to see if we could track this crack during its formation from its inception, that is from before the submicron stage, or from a crack opening, which would probably be in the sub-micron level range. So this is the baseline signature that we send into the actuator, and then we listen to the signal as we receive it at different receivers. So this is the PZT patch 2, which is sitting on the other side of the crack here. Now this is the notch, so the crack would grow from here. We are sending the signal in 1. This is the input signal, and the received signal at patch 2, when this is the cracking. So when the crack opening at the bottom was around 40-50 microns, this is the crack that has formed, and in the stress wave path, the crack opening was about 12 microns. So this is the change that was recorded in the receiver, which was station 2. Now, if we continue this, as we grew the crack, as the crack was opened, and when the CMOD, crack mouth opening at the bottom, was 100 microns, the crack opening displacement in the path of the stress wave was 36 microns. You see that there is a larger change in the received signal, and the change continues. So by the time the crack opens to about 100 microns, the received signal is, you can see that it's attenuated quite a bit. It's almost lost. And if we grow it any further, and suppose I make the crack 450 microns at the bottom, this is the crack mouth opening displacement, and the crack opening in the path of the stress wave is about 200 microns, then you can see that the stress wave is almost attenuated out. So basically there's not much energy going across the crack. And at this stage, in fact, you can visually see the crack. Up until that point, in fact, it's very difficult to distinguish the crack that's formed in the concrete. So basically we determined an attenuation factor measure. This is because when you have these stress wave measurements, oftentimes how do you infer what is produced by a change in the material path? So if I go up here, there is a change in the material wave path. I'm basically sending a stress wave from 1, which is the actuator, and receiving it at this 2, which is the receiver. Now, the stress wave would be affected by the stress wave path. There is attenuation of stress wave that takes place as it goes through this length of this concrete medium. Additionally, there is attenuation of stress wave that takes place in the epoxy layer surrounding the actuator and the receiver. What we are interested in is what is the change that is produced by the crack length. Now, to do that, I have to remove the influences of these intervening media, the concrete and the epoxy layers. And to do that, basically the effects of these material media appear as convolutions. Basically, they are convoluted onto the signal. So it's very difficult to pull them out in the time domain. So what we did was to develop a frequency domain measure, where basically we developed this attenuation factor based on a self-calibrating technique, which is quite used in ultrasonic stress wave measurements, which allows us to determine the change produced by the crack opening in the stress wave path. And now I'm looking at changes produced in the stress wave paths using different actuator receiver pairs. So first, if I look at actuator 3, which is here, and receiver 2. So basically, this is in the clean here. The crack is here. I'm sending the stress wave here, and I'm receiving it here. So what you see is that because there is no crack or no change in the material path between 3 and 2, as the crack grows, we see that the attenuation factor doesn't change. It remains flat. It's basically equal to 1. But now if I look at path 2 to 4, this is basically when I'm using 2 as the actuator and 4 as the receiver. So now the stress wave would basically cut across the crack. And so here I expect to see a change. And you see that by the time I get to a 40 micron crack opening at the bottom, and a 12 micron opening directly in the stress wave path, there's already attenuation. So the attenuation factor is already decreased. And as I continue to grow the crack, basically the attenuation factor continues to decrease. So we are able to track the crack opening very clearly with this particular measurement. And so we are able to basically locate cracks which are down to almost 10 microns or so. So crack openings of, in fact, this should be about 10 micrometers can clearly be detected using these PZT patches. So these are the, and of course, then we take the stress wave path between 4 and 1, which is also on the other side of the crack. We see that there is no change in the attenuation factor. So using these PZTs now, what I have is a methodology where I can adopt a cradle to grave measurement or monitoring system for concrete structures. The idea is quite straightforward, is that we put these sensors into concrete at the time of casting. So as the time when the concrete is being made, at the time when concrete is being poured. And then they would basically give me local information about the concrete, because as concrete ages, I can look at the impedance signature and infer about the stiffness of the material medium, the mechanical impedance of the material medium. So I can check to see if concrete has gained adequate strength. If it is, if I can open the structure for use, I can do local monitoring of the concrete structure as it is aging, as it is gaining strength. Once concrete has gained sufficient strength, I have now these listening posts inside concrete, which I can use for vibration monitoring. And I can use them or use them in any vibration monitoring scheme to infer the health of the structure. And finally, because these are not very expensive, I can in fact distribute these sensors around concrete and use them as arrays of actuators and receivers. So for ultrasonic stress wave measurements. And I can do like a tomographic kind of a measurement where I can continuously, in fact, inspect the structure to see if there is any damage in the structure, whether it is damage in the form of distributed damage in compression or localized damage in the form of cracking in wherever I have tension in the concrete structure. So that's the idea of using these embedded sensors in concrete by understanding the physics of the PZT sensor as it's placed in inside concrete material, which is an aging medium. So with that, I'd like to conclude. Of course, I'd like to acknowledge the people whose work I'm presenting here. Dr. Arun Narayanan, who's a PhD from IIT Hyderabad, he finished his PhD in 2018. And Dr. Amarteja Kocharla, who finished his PhD just a few months back. They contributed immensely to this presentation that I've made today. So with that, I'd like